this professor, I was his PhD student. I was his teaching assistant for general relativity, so I've used this book quite extensively, and it shows. So yeah, there is a connection between gravity and curved space, right? This is exactly the whole topic that we discussed during the main lecture of last Tuesday. So what we discussed was the fact that in non-inertial frames, things behave as if there's a force acting on this thing. We could argue that this force, this fictitious force, is indistinguishable from feeling a gravitational force. And we also saw that that means that every single object that is being pulled by the fictitious force or the gravitational force must follow the same path, right? So gravity, that's yet another way of saying this exact same thing. Gravity does not distinguish between different types of objects. And that's a version of saying the weak equivalence principle. Now, there's a stronger version. You might have read it in the synopsis that I posted 2 days ago. There's a stronger version, and that is that maybe gravity doesn't distinguish just between masses. All masses are being pulled the same way in a non-inertial system or by gravity. Maybe every single thing, so even things that do not have mass, have the same property. Now this is much more difficult to test, do you agree? I mean, we had this thought experiment, or in practice you could do this. You take a space shuttle somewhere high in the universe, you take 1 billion objects, you all drop them and see how they fly, and see if they all fly in the same way. That will be a test of this weak equivalence principle, whether masses are all affected by fictitious forces, or if you want, by gravity. But it's much more difficult, I guess, to drop objects that do not have mass to begin with.
But didn't the Paddington experiment in 1919 prove that the light is curved when passing?
Yes, absolutely. The 1919, yes. In fact, if you want to know more about this, on the 20th of May, in the headquarters of the Dutch Royal Society, there's going to be a whole series of evening lectures to commemorate that it's 100 years ago that light was bent for the first time. Including, by the way, this professor of astrophysics of the Brownian aperture is going to give the opening speech, and 3 other good speakers. And I myself am moderating, so I'm the guy telling now the next speaker is such and such, and now the next question comes from this young gentleman in the front row. So if you want to know more about the bending of light, absolutely. But that experiment just tells you that light is bent, which, if you want, we all know about the 1919 experiment, by the way, right? So, I mean, do you or don't you? This is important.
I don't.
Okay. Okay, it's a little bit off tangent, but that's fine. I mean, it is interesting. So, when Einstein came with this idea that gravity can be described by a curved space, he came to that conclusion by, well, the equivalence principle, that masses all follow in the same way. Right? The same argument from Tuesday. If masses all follow in the same way, then maybe you can describe the path that masses must follow as something as a property of the space on which they travel in, and not so much of the masses themselves. So that would be the weak equivalence principle, and Einstein promoted the weak equivalence principle to something higher that he called the strong equivalence principle, namely that the same effect applies to all things in gravity, so including light, say. And there's even a stronger version than that, and that says even gravity itself has to obey the equivalence principle. So, depending on which author you read, the nomenclature is something like this. Weak equivalence principle applies to masses. You have some middle weak or middle strong equivalence principle applies to masses and everything else except gravity. And then you have the strong equivalence principle that says every single thing in the universe must obey the curvature of space-time. Now, so Einstein, yes.
What is every single thing? I can think of light and mass.
Force carriers, quantum mechanics, things that cannot be expressed necessarily in tangible objects. I mean, even if you do your basic Schrödinger equation quantum mechanics, where you've taken masses out of the situation, there's masses in there, but the way masses move goes by a probability function that itself evolves in space and time, right? That thing itself, the Schrödinger wave function, also has to obey the curvature of space-time. That is not a triviality. Right? In quantum mechanics, the moment that you can really talk about masses as tangible objects is only after you've done your measurement, after the wave function has collapsed or something like that. But that before that stage already, wave functions themselves have to obey the curvature of space-time is certainly not a triviality. The weak equivalence principle in those terms would say, after measurement, in quantum mechanics, masses have to follow the curvature of space-time. But a stronger version would be, no, even before masses have become tangible, before collapsing of wave function, already then they have to follow curvature of space and time. Now, and then the strongest version is, and gravity itself also have to obey that rule. So suppose that you would have gravitational waves, that gravitational waves also, who themselves are curvatures of space-time, as we will see in one of the final lectures of this series, that even curvature of space-time has to follow some other curvature of space-time. So that's a stronger statement still. So the equivalence principle comes in 3 varieties, if you will. And the weak one is the easiest to test. Yes, you just drop objects. And the other ones are more difficult. So here's the Eddington experiment that Giovanni was talking about. When you take this middle strong, let's take that nomenclature. You have to take that middle strong equivalence principle that says, well, other things also have to follow the curvature of space-time. That would include light. Then Einstein said, well, okay, that means that if you have a very massive object here, I mean, I'm sure you've seen these pictures before, and you have a source of light at this side, then Newtonian physics, Newtonian optics or so, would say that one ray of light would just follow straight paths, yes? And there's many more, of course, but I'm just drawing these 2. These are the important ones for my story. But if space-time really is curved here, then that means, and not just masses have to follow that curved path, but light itself also has to. And that means that it's being curved inward. And that means that if you are here, this is my attempt at drawing an eye, you would see from that side and from that side the light coming from the star behind the mass that otherwise in Newtonian optics would have been invisible to you. And also, that works in many other ways as well, of course, because there's also a light ray going in the, in this plane. And it would also come from this side. So that means if you would look at this mass, and there is a source of light behind it, you would see a halo around this mass. Right? Because there's always some light ray that is being curved inward, and if you do this from all sides, you get a halo.
That's what's happening in the black hole picture, right?
Yes, in the black hole picture, don't we live in ridiculously beautiful times? Every week there's a new discovery on black holes and curved space-times and so. Yes, the black hole picture for a week and a half ago actually shows you that ring. But even if you don't take a picture of a black hole, but you take pictures just of galaxies in the universe, you also see, I don't have pictures available here because I wasn't expecting this little discussion, but we can look it up in the break. But if you look at Hubble pictures of just the universe, not focusing on black holes, you see many of these, there's a galaxy somewhere, and you see this ring of light around it. That ring of light is not due to the galaxy's own halo, that the thing that he produced himself. It's literally the light that comes from behind of it. And astronomers, like Professor van der Heuvel, take the amount of ringness here to calculate how much curvature there was due to this galaxy, and therefore what the mass of the galaxy was. That's one way of checking that there should be dark matter, right? Because you can estimate how many stars there are, about how many galaxies or stars you see within that thing. You add up what the mass is. You also calculate with general relativity how much curvature you need to make this big halo, and the numbers do not add up. That's one way of checking that there is hidden mass there, mass that does not shine out light. Now, this is now standard procedure in astronomy. But Einstein, who came up with this idea that something like this should exist, said, well, how do you check this, right? That was in a time when spaceflight had not been invented yet. So, what do you do? So Einstein came up with the following idea. He said, well, suppose that this mass here is the sun. Now, the sun has a big mass, right? It's 2 × 10⁻30 kilograms. That's enough to make space a curve around it. And that means that stars behind the sun should be visible by you by the bending of light. But here's the crappy thing. This starlight is completely swamped by the sunlight. This is why you do not see stars during daytime. They're there, it's just the sunlight is much more strong. Then Einstein thought, you know what? Suppose that you're in the happy situation that the moon makes a solar eclipse. That pushes away all the sunlight, but this light can still go around the moon and you would still be able to see the star. So Einstein said, well, if this effect is true, then that means the only thing you have to do is wait for a solar eclipse and just see whether you can see the stars that you know from your star mass that you know should not be viewable because they should be out behind the sun. He even calculated, Einstein, that if you would see this star, your mind would think that it is here, right? Because your mind thinks in straight lines. But your star map, because you already knew that the star was there, tells you that it's there, means that there's an angle in between. He calculated the angle, Einstein, just by using general relativity curvature of space. In fact, this is very likely exercises that we're going to discuss today, how you can calculate these sorts of things. So Einstein calculated that angle, and it just so happens there was a solar eclipse 3 years later in South Africa.
No, in Brazil.
No, there were two. There was one in Brazil. That expedition was completely marked by all kinds of crappy things. I mean, there's a beautiful story. I forget the details, but it was something like the expedition there. I don't know. They were abducted by cannibals, and they got
there was also one in Russia before.
There was. I didn't know about the Russian one.
Yeah.
You also know about the Brazilian one, right?
During the war. No, I didn't know about the Brazilian.
There is one completely failed expedition. I forget the details, but. Maybe they were not abducted by cannibals, but there was something along those lines, that there was some tribe that broke their materials or something like that. Something we should look it up. You might but I forget what the details are. The successful expedition was when an Englishman, Sir Arthur Stanley Arthur Eddington, I always forget his Stanley Arthur Eddington, who was a proponent of general relativity. The one who famously said that there's only two people in the world who understand general relativity, meaning himself and Einstein. There's a fun anecdote there, but let's get back to it. Many tangents here, but it's just such a rich history, really. You should go to this 20th of May event in Amsterdam to hear all about these things. Now, anyway, they did this expedition, this Eddington guy. He led the expedition into South Africa. It was on the 29th of May 1919, and they did the measurement, and Eddington measured this number. So he just measured where this star was as seen from the Earth, or where you thought it was. He knew from the star maps it should have been there, calculated the angle, it was Einstein's angle. Now when Eddington reported this to the scientific world, this is when Einstein became world famous. He was already well known in physics, in the physics community. But all of a sudden, you could see that something was wrong with Newtonian physics, right? In Newtonian physics, this line would have been straight, because Newtonian physics says you can only bend things, Newton's second law, if they have mass. Light doesn't have mass, blah, blah, blah. So there was a huge front page news all over the world that physics had been wrong for the last 300 years. And there's a very fun New York Times front page article on that, and it says, heavens do not appear where they are, lights askew in the heavens. And it says with a little caption, but nobody need to worry. Because people might read this and think, wait a minute, so everything is wrong, everything's going to collapse and everything's wrong. And then Einstein became world famous, and this whole idea that everybody, the fact that you can now say Einstein is synonymous with very intelligent person, he really came from that event. He was known throughout the world ever since. A little fun extra anecdote, Einstein said that ever since those newspaper articles in 1919 and onward, he could not walk the street anymore because people would ask him in the street about these sorts of things, and relativity and blah blah blah. And then Einstein came up with an idea to, not constantly be pestered by people asking him about relativity. So he said that when somebody would come up to him, he would say that oh no, I'm always being confused by Professor Einstein, or for Professor Einstein. Now think about this, you are a German person living in the United States. He has a very strong German accent, you can YouTube the guy, right? With this electrified hair, and then you try to pass on that you are somebody else. How many strongly German-speaking people in the United States have exactly this look? So he pretended that he wasn't Einstein. Anyway, so this is how you can see that space-time is bent, and that it operates not just on masses, weak equivalence principle, but on other things as well. Okay? Now, again, a little bit of a tangent, but very important. We also now know that the strong equivalence principle, the one that says even gravity itself has to obey by these laws, also applies. And that has to do with this binary neutron star from a couple of years ago. Namely, the binary neutron star of the 17th of October 2017. Binary neutron stars send out light and gravitational waves. And that means that you can measure this event both by your optical telescopes and by the gravitational wave telescopes, and of course they did. The first one that picked it up, that was the gravitational wave telescopes, the LIGO detectors, in October 2017. And then the astronomers quickly pointed their optical telescopes there, and by the arrival time of the light that hit the Earth and the gravitational waves, you could tell whether they arrived at the same path and also at the same time. That is an extremely strong test of the strong equivalence principle. If there would have been deviation, you would have picked it up. Even if there was an extremely small deviation, that event was many, many millions of light years away, even if there was only a small deviation, say gravity travels a little bit less fast than light does, for instance, over, I forget what it is, 50 million light years or so, maybe billions, you would expect that to be a cumulative effect, yes? Yet the difference in arrival time was only of the order of seconds. You can calculate back how small of a speed difference there must have been between the two effects, and it was completely negligible. Which is really another way of saying gravity and light really were affected by the gravitational curvature in between the binary neutron star and the Earth in exactly the same way as far as we can measure. So that was really one extremely strong test of the strong equivalence principle. Now, as of yesterday morning, we can do that same test again. I can tell you, if you find a deviation from the strong equivalence principle, that's probably another headline news. Well, maybe not headline, because who knows the strong equivalence principle, right? But it will be new, very big news in the physics community, at least. But I'm not expecting this to happen.
So you're measuring a gravitational wave and also light?
Yes.
Okay.
And that's easy enough, right? Light we've been able to measure many years ago. So here's why binary neutron stars are so important. You can not just test the specifics of that particular neutron star, this binary system, you can test the specific of space-time in between as well. And many more things, by the way. Anyway, huge, huge effects. So, now that's kind of a nice warm-up, right? So we now understand why curvature, the mathematical description of curvature, is important for your description of gravity. We saw in the lecture, gravity can be described as a curvature of space-time, so we need to study how do you describe curved space-times. You remind me, what exercise?
5, 6, 7, 8.
5, 6, 7, 8. One of them is the egg exercise. The exercise, if you will. Okay, it's Friday, but this is about as funny as I will get today. Yeah, I know, it's crap. It's crappy joke. Crappy.
Disappointed from it.
Good. You will have to remind me. I vaguely remember we have to calculate the circumference of a circle that lives itself on a sphere. That was the exercise, yes?
The circumference? It was the area.
Yeah, it's the area.
Oh, it's the area? Okay. Alright. Okay. That's fine, we can do both. Let's start with the circumference. I think that's a little bit easier to show, and then the area is very easy. Now, what would the circumference be if it was not a curved space-time? So if you know the radius of that sphere, what would the circumference be?
2 pi r.
2 pi r, yes. And the area?
Pi r squared.
Pi r squared. Okay. Now, if you recall, one way to test whether the space-time is curved is by checking whether your usual rules of geometry hold. And we talked about the sum of the angles of a triangle should be 180 degrees. If not, then possibly you are in a curved space-time. By possibly, I mean you haven't made any measurement mistakes or so. But you could also just draw a circle, draw its radius, measure its radius, measure its circumference, and check whether it is 2 pi r, or its area, or whether check whether it's pi r squared. If not, curved space-time. So we don't have to travel away from the curved space-time to see whether things are curved. But it would be good if we had expressions for this. So let's draw the curved space-time. X, Y, Z. I think the exercise says that the space-time itself has radius A. Okay. Voorslagen. Suggestions how to do this?
Well, we start from the line element.
Okay. Now, you have your line elements. Oh, what I'm saying now is something that you know by now, yes? You have this line element with this metric tensor in between. This metric tensor tells you how Pythagoras theorem will typically look on this curved space-time. We even know, because we calculated ourselves, what this metric tensor is for this particular curved space-time. We calculated ourselves a couple of days ago, so you might remember it by heart, maybe you don't, maybe I've written in your notes. Right? Your metric tensor tells you how your space-time is curved. And we calculated what the metric tensor is for something or someone that lives on the surface of a sphere.
Okay.
0 r squared and r squared sine.
0? Did you say
Oh,
zero?
r squared.
R squared,
It starts
r
with
squared
okay.
sine squared.
Yes, but be
So
careful, you know it's a
it's-
squared now, right?
Yeah, true.
Okay. And this is a squared sine
Sine
squared
squared.
theta. And then theta will be the angle with respect to the z-axis. Okay, so this is our metric tensor. You don't have to worry where this comes from. We proved this a couple of days ago. This is really the metric tensor of the surface of a sphere. The metric tensor contains all the geometric information that you want of your space-time. Once you have this object, you know everything that there is to know about the curvature of space. Okay, you have to try it out maybe, do some maths on it, but this tells you everything. So we have our line element, and maybe it's good to repeat a little bit something of a couple of days ago. If you have your line element, this ds that you have here is the distance between 2 points on your curved space. Which 2 points? That's up to you to decide depending on exercise. So if you have 2 points, I called them P and Q last time, somewhere on this sphere, and you want to know how many meters are there between P and Q. Literally, if you would have a measuring rod, it should be a curved measuring rod, but you know what I mean? If you would measure how many meters is between P and Q, this is the ds numbers that you're looking for. Okay? Do you know how we get a metric tensor to begin with? We did it a couple of days ago, but it's good to repeat maybe, just for a moment. How do you get a metric tensor? If I give you a curved space-time, how do you get a metric tensor? Because yes, this I'm going to ask you on your midterm next week, yes? So it's good to repeat this for a moment.
Well, you go the other way, no? You can try and calculate what the line element would be by first principles, so to speak.
Yeah, how?
Well, you, for example, for a sphere, you can think that along the z-axis, a distance is given by d theta times r along the z-axis. So,
oh, sure.
yeah,
But
if you want to say so.
is that something like this? R.
Minus r sinus theta e theta. Yeah, but not
This
wrong.
is correct.
Well,
yes.
but that's not what I mean.
Oh, that's not what you meant.
Yeah, kind of. I mean, you can see it that way. But just in my mind, if I imagine a sphere and I imagine what would be a distance along this direction,
Yes,
that would be just r sine d theta.
I see. Yes.
And then you try to measure what general distance along this direction is.
Yes.
Then it's the radius sine of this angle and d phi.
Yes.
And then that's the two distances, the squared of each would give you ds squared.
That is correct. Yes. Okay. No, that's exactly right. Now, to put that in a what you said is correct. Slightly paraphrasing, but what you could do, and it really this is what Simon was saying, but is that you say, well, any distance, in our case, would be something like this.
Yeah.
Yes? Any distance can be written with Pythagoras theorem if you square it. Agreed? What you then do is that you say, you know what? My x, y, and z in the coordinates of the sphere are given by x is something with an r, a theta, and a phi. Y is something by r, and theta, and a phi. Z is something with an r, theta, and phi. Well, not a phi in this particular case, but generally you can write these coordinates into the coordinates of your curved space. And then you literally just calculate your dx, dy, dz in the new coordinates, work out the thing, and you will get a new Pythagorean theorem, but now not one that says dx, dy, dz squared, but you will get, in our case, the r squared, the theta squared, the phi squared, with some numbers in front. Those numbers collected together is what defines your metric tensor. That's how you do it. So, yes, you can expect an exercise in the exam where I say, well, look, I have this curved space here, give me the metric tensor. I expect you to go through this calculation, okay? Now, one thing that I feel I had not really expressed enough on Tuesday during the tutorial was why you can use this as a starting point to begin with. So I feel that in doing this exercise I should emphasize this, because I start with Pythagoras theorem, right? But I also said that Pythagoras theorem should not even hold on a curved space-time. So why is it that I start with a perfectly well-defined Pythagorean theorem to later on conclude that Pythagorean theorem doesn't hold anymore? Do you see that there's something strange going on there?
So, it's because you have the dx, right? If you approach it in a small location, you can still assume it Pythagoras theorem hold.
Yes, this is very important. So just to lay out the issue one more time, this strategy, what we do is that we start with the Pythagorean theorem as if it is a non-curved space-time, then calculate the metric tensor, and then say, look, the space-time is not curved, or is curved. That is very strange. I take a premise and then I conclude the exact opposite later on. Now, the answer is completely correct. Any space-time, if you zoom in enough, will look flat. If I draw a triangle here on the floor, you will not see the curvature of the Earth because I'm too up front. Yes? But if you would zoom out, or if you want to make your triangle bigger and bigger and bigger, at some point you will see the curvature of Earth. So this is why it's little d's here. You make an infinitely small snapshot of your space-time. The infinitely smallness means that by very good approximation, or mathematically speaking, by perfect approximation, your Pythagorean theorem holds. You calculate your metric tensor, then you get how your metric tensor looks infinitely small. And now you're going to zoom out again and look what it would look like if it were not infinitely small. Right? You will get your ds. And if you then want to have how it really looks, the zooming out part is an integrating of the infinitely small ds. That's the idea. So this is why you can use Euclidean space as your starting point, under the assumption that you work infinitely small, get your metric tensor, zoom out to your actual curvature, that means integrating your infinitely small. That's this last step. Okay? Now, doing the exact same exercise would result in this particular metric tensor for our sphere. Okay, good. Now, let's do the exercise. We have a metric tensor. So let me be so kind as to write this out for you. Or maybe you can dictate this, just to check whether you have the contraction down. I want to write this in terms of d thetas, d phis, and such.
Is a squared d theta squared plus a squared sinus squared theta d phis.
There you go. That is of course correct. Good. So we now know how to calculate, if you stick to infinitely small, what a triangle would look like on your curved space-time, but written in polar coordinates. And the question still stands. Yes, if we want to make this into an actual distance, so let's call that big delta S, the actual amount of meters, not infinitely small, it just means integrate this thing. Oh, and the square does not become a square root. Now, which distance is, well, whatever you put in, right? If you integrate from this p to this q, that means you have to choose your integration variables or bounds in a particular way. You have to choose how theta depends on phi in a particular way. That's up to you to decide, depending on exercise. So maybe that's the next question. If we want to calculate our delta S, our amount of distance, which distance are we now interested in? I prefer to do circumference one first, and then we can do the area. The circumference is a little bit easier to see on a picture. So.
I think it's also necessary.
Yes, because then you can integrate that thing, of course, yes. There's other ways to do it without the additional integration step, but you're right. But let's do the
thinking this is also sometimes called parametrization.
Yes.
And so that's the same thing.
Yeah, yeah, in maths you would call it parameterization. Because really this thing doesn't tell you that much yet, right? I mean, what are you integrating over? An integration usually ends with a d something, right? Now there's two of them, so which one are you integrating? In fact, that was your question 2 days ago. Does this mean that there's 2 integrations? No, there's still one. But it's up to you to massage that in a way that you can use your calculus on it. So visual representation of massaging your maths, okay, good.
Sure.
Well, let's start by drawing the thing of which we want to calculate the s, the delta s. So let's draw a circle on the thing. Any preference where to put this circle? Doesn't really matter because it's spherical, so you can choose any point, right? There's no difference between this point and that point on the sphere. It's S-curves everywhere. So I would draw the circle there where you think your mathematics comes out easiest.
Around the z-axis.
Yeah, that's what I would do. You don't have to. You can also draw it here at some random point. It's just not a very particular good choice given this set of axes. Alright, so that will be this one. And then it continues on the other side. This one? Okay. We want to know its circumference. Written as a function of this guy's own radius. Okay, so this thing has a circumference. Let's call that c. That's the amount of meters from here to the other side and back to its starting point. But we have to express this in terms of its own radius. The radius, I think the exercise wants you to call capital R. Where's the radius in this picture? Is it this? Just from here to the middle? I see a yes and I see a no.
Like
so
in a 90 degrees angle.
a 90 degree angle?
Yeah, if it goes like this. If the circle's
Okay,
here,
so
and
can
then
you
it's
keep
like
your hand up? In fact,
Yeah.
would you mind doing it on the camera? You can, you can visually, you can facially stay outside, but I need some hands here, okay? So this is the way of putting it.
That's it.
I will blur, okay? Okay, so here is where the sphere goes, yeah? This is the North Pole, if you will, of the sphere. This here is where the red circle is, this one. And you're saying the radius is from here to here. So that means not from the North Pole, but if you would dig from the North Pole downward to the, I also forget what it is, latitude or something like that, right? You would dig deep enough that you can make a 90 degree angle to the other side. That would be the radius. That is your suggestion.
Yeah.
At the same time, Simon, I see vehemently shaking his head. No, that's not the circumference, or that's not the radius of the sphere.
I don't think so, because the inside of the sphere doesn't even exist from the sphere point of view. So you cannot dig through the surface if you're stuck on the surface. How can you measure a distance that...
We live in a
assumes-
two-dimensional
yeah.
space-time.
Yeah.
It's hypothetical, sure, I agree.
Yeah.
But it's not literally like the Earth where you have to dig down. There is no other dimension.
Yeah.
What does this third dimension tell you in this case? It's just a visual mathematical representation of your curvature. It's not actual distance in which you can travel or dig or whatever. Also, if you are bound to live on this surface, this at the same point really is, you cannot be here. This is the only place, this is middle of the circle that you can get at the North Pole, right? If you're stuck yourself to the surface of the sphere. So that means you're standing here with this circle spreading around you. The North Pole is as middle as you can get in this curved space-time. So what is the radius? If you were this guy.
Well, from there to the circle.
Well, yes, it will be this distance.
Yeah.
Right? Just from where you are to where you see the red line. Now you can already see that this will not give you 2 pi r. So this distance is what the exercise wants you to call r. Now you can already see that it's not going to give you the relationship between that one and this one is not going to be 2 pi r. Joyce's choice. Here. That would give you, if you would have defined your r from first digging down and then take your 90 degree, that would be 2 pi r. So it's going to be more or less. Is the radius, is it going to be a bigger number if you live in a circle or a smaller number? A bigger number. So that means 2 pi r has to be corrected by a certain amount, yes? So we have to calculate really the circumference, this here, which I will call C, but I also propose let's calculate capital R. So let's calculate the amount of meters that this guy would have to measure to reach the circumference, and the amount of meters that the circumference actually is. We get two formulas, combine them with each other, and then find what the relationship is between circumference and radius. So that would be my strategy. So we have to do this exercise twice. One is going to be calculate the circumference. And once we have done that, we're going to calculate this radius, get two expressions, combine them, and get the relationship between C and R. And that's what the exercise wants from you. So pro tip, life hack, it really helps to make pictures of these things before you start calculating.
So in our dx mu that we have now, the first coordinate is the theta and the second coordinate is the phi?
Yes. Oh wow. So, which one do you want to start with? We have no choice but to go through both. Both of them requires this expression. It's just, this expression holds for any 2 points. We have to define our points properly. Any suggestion? Or any preference which of the two to begin with?
Circumference.
Circumference. Okay. So circumference is given by a squared d theta squared plus a squared sine squared theta square root integral. Okay. I just copied this one. Oh. Phi squared. Now what?
You will try to take d theta out so that you can integrate over d theta and you get d phi over d theta.
Something like this?
Yep.
Okay. By the way, you could have also taken d phi out if you would have wanted, right?
So it won't cancel that, right?
What is you? Which one?
From the z-axis, no? Isn't it just that one cancels out?
What cancels out?
One of the d's? Or am I just really?
No. So you, one of the d's would not cancel. You mean that it is itself zero, right? Is that your question?
Yeah.
Now, this can only be zero, or this can only be zero if this path along which you're measuring your distance does not change in that coordinate.
Yeah.
Right? Is that the case here?
Yeah.
Yes. Okay.
Yeah, near.
Okay.
Okay.
Good.
Okay. Okay. Okay.
So,
Then I'm falling. I was
so
like, oh
no, that's fine. So, which of the two coordinates, if you walk along this circumference, that is the path. This is this path that you're doing this. This is the circumference that you're integrating over.
It's the
So, which of the two coordinates happens to be constant?
one from the z-axis, but I don't know the name anymore.
Ah, yes.
Phi.
Theta.
Oh, it's
Right?
theta?
Because
Yeah.
this
It's
my God.
circle is at a
angle.
fixed theta, and then it circles around. The theta is constant along with it. Listen, the theta has some value, but the d theta is zero. You stay at that one.
Yeah, it's the same as what we did for
Yes, so Zeb's suggestion here to take the d theta out is mathematically correct. It's just for this particular exercise not the best choice. In fact, it's even unnecessary because you could already tell from the outset that this d theta was zero to begin with. So, what we get is a squared sine squared theta. Again, theta itself is not zero, yes? Theta is number such and such. D phi squared
I just forget which one's which one.
Yeah. Data is more like this.
Yeah.
It's 2. It's from 0 to 2 pi.
it's from 0 to 2 pi because the phi runs from wherever you want to start all the way to the other side. So there's a 2 pi that you do over phi. All the theta is constant. We agreed on that. The a is constant. That's just the radius of this hypothetical 3-dimensional sphere. So I get 2 pi a sine theta. This is the circumference of this red circle. Now, perfect. Do you see, by the way, that if we would have started, if we would have drawn the red circle here,
Oh no.
then your theta, it would be the same circle, the same final expression, but this particular choice, given this coordinate system, would have your theta and phi, both of them change in a very particular way to make this circle. Correct, not the best choice, right? To do this, pragmatically speaking. So it really pays to look at your picture and say, you know what, maybe this thing I want to draw, maybe here is a little bit better than over there. So we have our answer, we have circumference. Good, great. It's easy, right, John? Relativity. Look at this. Easy. All right. Now, how about this radius? Let me write down what the expression is going to be. A squared sine squared theta d phi squared. Just copy this one. Maybe we can just be as wise as we were a second ago. Maybe look at the picture first before we start our mathematical machineries. So the path that we're now going to follow is this path, from North Pole to that theta where the circle is. So let's call it the radius.
Well, you can keep phi constant.
Now we can keep phi constant. Because walking from here to here will happen at a constant phi. Now what that phi is, doesn't matter. The phi just defines whether you walk from the North Pole to this part of the circle or to the other part or some other part in between. That doesn't matter, it's a circle. Every single direction that you choose to take on your way towards the circle is going to give you the same answer. So along that path, now our phi.
Can we visualize phi?
Yeah, absolutely. This is phi. The angle that you make with the x-axis is phi. So,
okay, so
in the previous exercise, when we walked around the circumference, that really just means that you walk this distance. That's 2 pi. Now here, the phi is going to be a constant. But now your theta isn't, right? So, just by having chosen our red circle in just the right place to make the mathematics somewhat easy, it means the phi is now constant. That means that you get a squared d theta squared. You get this. Now let's do this integration. At what theta do you begin your walk if you start at the North Pole?
0.
Okay, so that's theta is 0. Where do you end?
At theta.
Well, whatever the theta is that you happen to have chosen your circle, right? So that's this theta. Mathematicians hate these sort of stuff. They will say, well, but then this theta is not that theta. Yes, you're right. Okay. This is theta prime or something like that. I don't know. Or call this a theta circle or whatever you want to do. Okay, so someone do this calculation for me. You will get this. Beautiful. So literally the amount of meters that you would walk from North Pole to here would be that over there. Would be that distance. And the amount of meters that you would have to walk from here to there, right? You have your Apple Watch or something like that that tells you how many steps you have taken. That number would give you, that number would be this number if you walked along the circumference, and it would be this number if you walked along the radius. Okay, we have our two expressions. We have our r, we have our circumference. That was not the question. The question is, how are they related on this curved spacetime?
You can plug one into the other.
Multiply.
This, by the way, is
Yeah, exactly.
Okay, good. Yeah, sure.
Oh, it's gonna be R.
So
That's what I got.
maybe let's go for the expression. Circumference is of capital R. Let's see if we can get that expression out. What I see is 2 pi
Just
a
substitute.
sine theta, but we saw that
R
theta is
over
R
A.
over A. So apparently it's this. This is your relationship between radius and circumference on this particular curved spacetime.
Okay, that made it easier.
Note that it's not 2 pi r. Also note that if you lived in this spacetime, you didn't even know about these calculations, you would have drawn a circle on the floor, you would have walked around it, you would have measured the radius Apple Watch or something like that, and the circumference Apple Watch, and you would have found this expression. If you were smart enough, you could have calculated back that apparently your space was spherical. If you were smart enough. So.
And precise enough.
And yes, and the circle is big enough, because you would think that if the circle can be drawn very small, and you would still see this effect, then probably you could have seen by sight alone that you live on a sphere. Okay.
Exactly.
But let's suppose that you're a blind person, and you can only hear your footsteps. Then this would have told you that you lived on a sphere. Oh, fun extra exercise. Let's check our starting premise that if you zoom in enough, you would get back your something that resembles flat space. Right? If you draw your circle on a flat enough, or if you draw it on a flat enough space and you zoom in enough, you probably at some point would have a difficult time seeing the curvature. So
So when
Goes
how do we zoom in mathematically, given this expression?
It's really small.
Well, what goes to what?
No, not A goes
Sine.
R is much smaller than A.
Yeah, R
Yes.
is much more.
No, let's see what happens. Do you happen to know your Taylor series for sines? You know, it's the sine of x for x being very small.
Well, you can guess it from
Yes,
what-
yes. But suppose that let's go with the math. Let the math lead. Okay. Do you know from your calculus the sine of x for x is very small equals?
1 plus cosine.
No, that would be
One
cosine.
cosine.
Yes. Write down a Taylor series, this is what you will find. Now we have a very small x here, right? Because if we zoom in enough, that makes our radius of our sphere on the floor much smaller than the curvature radius, a. So if we read this as x, you will get 2 pi a. Let's take the series will give you, not because I want to get to this particular answer, because mathematics tells us so. It will give you x, which is r over a. Well, 1 minus 1 over 6 times r a to the 3 plus extra terms. 2 pi r. So, if you zoom in enough, you do actually get your Euclidean rules of geometry back, exactly as you would expect on physical graphs. That's nice, right? I find this pretty cool. It also justifies that we started with this infinitely small Pythagorean theorem as if it were a flat space. That's still retained. You can see that it checks out. So everything's fine. So that's how you do it. Any questions on this? On the strategy? How this was done? Right, you know your metric tensor, you know your general distance G2 points. Depending on exercise, choose your distance carefully. You might want to make a drawing so you know exactly where to put things to make your mathematics, your life easy. Go through the math, get your result. This was not the question. We had to calculate an area.
Integrate.
Yes, we integrate because we don't want to know this amount of meters. we want to know this amount of square meters. So you cap this upper part of your sphere. How much square meters of paint do you need? How to do this? I heard mumbling and I saw a thing.
Like integrate over different values for this one. The theta.
Theta, yes. Because for every theta using this expression, well, it's not written in terms of theta anymore, but fine. Principally, you're right. For every theta, you will get a circumference.
Mm-hmm.
But that means if you add all the circumferences for all the thetas in between this one and all the way up to the North Pole, the sum of these circumferences is by definition the area, right? So, if we want to turn this into an area, integrate over all circles in between this outer circle and every circle in between all the way to the North Pole, and you get your area. Should be easy. Don't need these trivialities anymore. Here's the area, let's call it A. You dictate, please. Gave you the strategy, you need somebody to tell me what to write. Scribing here.
So it's the integral from theta c to 0 of the function that we had for the circumference dt.
Yes. But it is this, it's circumference, integrate over theta from theta c here to theta 0. We have our definition or our expression that we calculated ourselves from 0. This gives you 2 pi a sine, well, there's r over a, but we saw before that you might that the original expression for that was theta. So we're just going to put negative theta.
Question.
Yes.
Why are we integrating from theta c to 0 and not the other way around?
That's a good question, because you can get this area either by, if you want to paint the floor, yes, you can either start from the outer circle and then circle yourself all the way to the North Pole, or you can start in the middle and then circle outwards.
But don't we have a problem with the sign?
Yes, mathematically speaking, yes, you would have a problem, because in one case you would get a minus sign extra, but you know, we're going to be physicists and say it's an area absolute value. But you're right. I mean, but you do see that the amount of square meters doesn't care whether you start with the outer circle and then painted your way inward or the other way, right? Pragmatically speaking, I think you want to start from the inside and go to the outside, because then you can go do something else while the paint dries. Right? The other way, you would have sat in the middle and you would have waited. Yeah, you see my point. So let's not worry about minus signs here. Can somebody do this horribly difficult integration for me?
No? Yeah. He's always like math. I lost that.
Just sign
Minus
changes to
cosine.
cosine, minus cosine.
Okay. So we this.
Minus 2 pi.
Cosine
Pi a 1 minus cosine. See.
No, we can do the same with the Taylor series.
What?
Oh yeah, that is nice. I wasn't even thinking about that, but we could do. Yeah, let's do that. No, but here's your exact expression. No approximations. This is completely right. But before we go to Bring, let's take the old muffles approach, as it is called, and say, let's look at what this would become at the moment that you would be on a flat space, or approximately flat space. Okay, so this is the exact expression, just like this was the exact expression. Let's see what happens if we zoom in on this particular circle so much that you can hardly see the curvature of your space anymore. So, I have my area, which is 2 pi a, 1 minus cosine phi, this one. Was that part of the exercise to do this approximation, or was this your own? Good. Oh, it's fine, let's go for it. Okay. We already saw that this is really r over a, yeah?
Yeah.
Okay. Zooming in, we also saw that before. It just means make your circle that you draw on the ground very small compared to the curvature size of your space. So r is going to be very much smaller than a. Okay, now let's take our series our way here. What is cosine x for small x?
1.
I hear a 1 minus, I'm taking it. What is the minus part?
X squared
Over 2.
I was so hoping that this would come from, I mean, I see conspicuously both of you looking at a screen there.
No one knows it. So.
I do. It's a very basic Taylor series. There's more terms, yes. This,
Oh, you were.
and also, really, it's a pattern easy to remember.
Wait,
Is
Anyway.
that a plus or
wait,
minus?
what's the pattern then? Is the other one?
Is
What?
the last
Are
one
you
is a plus or
serious?
minus, right? Okay.
This one's 4, 6.
Anyway,
Yeah.
we're
but
zooming in
each
enough
one
that
has their
this is
own-
going to be a good
Each
approximation.
function has their own pattern.
Yeah, no, but I
Yeah,
was
of
wondering
course.
for. Yeah, okay, that makes sense.
So let's go with this approximation. You will get 2 pi a 1 minus 1 plus x squared over 2. The x being here r over a, so I get 1 over 2 ra squared. And if you want, you can add more terms.
So it's 2.
These drop out. I get 2 pi.
Very missing.
This one drops out. I get an a. You got a 1 over.
Pi r
Oh, yeah.
squared over a.
So I get.
But you still have the a, no?
Very missing in
A superfluous a.
There should have been
Should be no
2 pi
a.
a squared at the beginning. That's what I had in my solution. Because when you integrate, the theta itself is a function as an a inside.
Yeah, you're right. Yes.
So if you integrate with respect
Yeah,
to r,
sorry guys, I was a little bit too fast here.
yeah.
We integrated over the theta, but the theta itself was an r over an a. And instead of integrating over theta,
Yeah.
you could have integrated over the r from here to there, and it would have given you by the chain rule an extra a.
Yeah.
I was a little bit too quick. I wrote as if theta was completely the same thing as an r. It isn't. There's a factor of a in between, and by the chain rule that were pops up. So sorry guys, there was an a square here, was an a square there. Really, it's really just these series of steps, but now write it please as r over a, do that integration
Yeah.
instead.
So, because A is constant but R is
The differential is going to be
then
Then this would be the r.
GR.
the I, right?
Yes.
So the boundaries go.
The boundaries go from the r, the outer r, to 0. And by the chain rule you would have gotten an extra a. So
Yeah.
thank you for the correction, yes. So you see my mistake, yes, integrated over theta, but theta itself was secretly a dependent. I just took out that part. Yeah, it was very sneaky theta. So this is, here comes with the square. Good. Okay, now going back here, all of this is still right. We corrected for the missing a, we get this. Taylor series, all fine. The 1's drop out. The 2's drop out, I get a pi, the a's drop out, I get pi a squared, exactly as you would expect. If space-time had been flat, then this area would have been pi r squared. So, it all checks out.
How many Taylor series all those can you use before it doesn't show?
Oh, the next one already messes it up, because the next one would be x over 4 factorial. So you would have got here an additional minus 1 over 24 r to the a to the 4, which would have given you an extra term.
I'm just thinking the first order is just a flat line by itself anyway, so then you would already expect it to look flat. See what I mean?
Not really, no.
So, no, maybe I'm not making sense.
No, maybe you are. It's just
I'm thinking
I'm
the first order Taylor series is just a flat line anyway. So
Oh, yes.
then if you just use the first order, of course you're gonna approximate as if it's a flat surface around this
Yeah, but
area.
by first order, do you mean this one?
Yeah.
Because if you would have only taken this one, then the area would have been 0. Because then this one would have cancelled this one,
Mm.
would have been 0. But that makes sense to me as well. Because it means
Yeah.
you're zooming in too much.
Yeah.
You're making your circle so small that the thing has no area anymore. So, it's actually quite easy, right?
Mm-hmm.
Just have to get used to manipulating these line elements, but there you are. So we are now in a position we can describe curved spacetimes. And exactly as we promised on Tuesday, using just the metric, without having to zoom out or move out in some additional dimension and look back, we can calculate deviations from Euclidean geometry, from flat space. Here's your deviations, this part and such. And you can determine that you live in a curved space-time. Perfect. That means in our next series we're going to describe gravity. We have two ingredients. We now know how to describe curved space-time. We also have seen that curved space-times have something to do with gravity. Next week on we're going to put that together. And you can describe how gravity exactly looks due to this curved space-time. That's the idea. Let's have a break.
What?
Well, behind literally and figuratively.
Yes, that's true. Okay. So there's the egg.
You know what? Sorry, I can't do everything. You might need the rest too.
Yeah, that was easy.
You end up with angry emails from biologists.
They won't mind an egg.
That is a good point, actually.
It's an organic object
Yeah.
made of cells. So this is like a general expression as a function of theta.
Mm.
We want to find an appropriate f of theta that would define this egg. So what the book does, and other examples with other shapes, is they look at properties of the shape itself and try and translate that into relationships between the variables. So for example, you could say that the circumference for any constant theta, which would be like the lines of latitude going down, would tend to increase and then decrease at the end. And have its maximum probably somewhere closer to the bottom. You could.
Do you have an expression for the heights? No, we have to plug that. Because like where the maximum is gonna be is gonna depend on the height. So
Yeah,
that's gonna be in
true.
there probably.
Well, depends on what shape egg you have.
You start drawing, axes and like
Yeah,
big
yeah.
wall, like 5.
Okay. So okay, let's say the circle that I drew is the maximum and center the axis on the egg.
Okay.
Yes.
Does that make sense?
Mm-hmm.
And then for any point on the egg, you have the theta, and you have the phi.
Then you need to have another point with d theta and d phi. So now your point is phi and theta, and then you need to compare it to another point that has phi plus d theta.
You need 2 points with a d phi and a d theta.
But then
And a dr in this case because it's not a sphere. You have different distances from the center.
mhm.
So E, Q, ds.
and the angle between the lines, the line at P and the line at Q is d theta, right? Because you define Q as having the coordinates of P, which are theta and phi, plus the difference, which is d phi and d theta.
You define it to have a constant phi.
I mean,
You can. You can define it anyway.
yeah. It's just that like you have this difference that you express with the d phi and the d theta.
Mm-hmm.
That's what they did with the
And
sphere
the
as well.
dr
True.
as well.
Yeah, that's something that I can't really wrap my hand on.
I really don't know how to get the function.
We can use the one that the book provides.
What does
If
the
you
book
want.
provide?
1 minus theta over 2 pi.
Where did it say that?
It's in the solution.
Yeah, have access to privileged information. So what do we think it is?
1 minus theta over 2 pi. But I have to tell you something, Gideon, because I put this on the web, but on a program, and it didn't seem like an X shape.
No, and I am very doubtful that this will result in an X shape.
But seriously, that was the solution provided.
I believe you. It's just I do not see an egg coming from this because
Yeah, me neither.
your theta. Now look at this. Your theta going from 0 to the other side, to pi. Now if you go around once, that will give you the 2 pi. Actually, no. Okay. No, I had a particular objection, but I don't think my objection holds.
Well, when theta is 2 pi, the function becomes 0. And when theta is 2 pi, that would be at our maximum, at our equator. Here.
Yeah.
But I'm not sure what that means in terms of... That means that ds is just a d theta. Is this supposed to be squared?
Yes.
Yeah.
Yes. No, you can. Line elements always come with the two d's multiplied with each other.
Yeah.
Right. In our particular case, so far it has always been one thing multiplied with itself. It might be combinations of these.
So would it make sense that at theta equals 2 pi, ds is just a d theta? It doesn't have a phi dependence. Yes, that does make sense. Because f becomes 0 at theta equals 2 pi.
Yes. No, you should.
This looks more for the two-dimensional case.
Well, maybe
F theta.
let's start there first. The exercise is about a space-time where you live on the surface of the egg. Yes.
Yes.
Okay. So how big is our metric tensor going to be? How many rows? How many columns? Two. Yes, because it's a two-dimensional space-time. The surface of an egg. Okay. Now you wrote down. It's a good thing to investigate this starting expression for your line element. It's a very particular one. You write a squared d theta squared plus some unknown f.
But in the case of the sphere, we had the radius being constant.
Yes, but here it is certainly a is not going to be constant.
That's
It's not
that's
constant,
not
that
too
would
very
No,
much.
I mean a is this distance, but you can immediately tell the distance is biggest here, and then it slopes downwards. I mean, as theta becomes bigger, this number, the a at theta pi over 2, is certainly a smaller number than a was at theta 0. So the a certainly, in order to get a shape like this, must be theta dependent.
Does that not imply a 3 by 3 metric tensor?
No, because you're not increasing the amount of coordinates. You haven't introduced a third coordinate. You just said that one of the existing two coordinates appears at a different place as well.
But now they're... So what are the two coordinates, phi and theta?
Yes.
Then what happens to r or a?
Well, you can immediately tell it is going to be a theta dependent function.
Yes.
How it depends on a, well, that is exactly the exercise. You have to choose, one of the things that you have to do is choose an a as a function of theta that makes this particular shapiness.
Okay.
Aside from that, you still have to pick your f in a way. It's a very open exercise, right? There's multiple ways to get something egg-like.
Well, a is at a minimum when theta is at 2 pi, and at a maximum when it's at 0 or pi.
Well, a is never going to be 0, right?
I mean when theta is at 0.
Okay. Okay, so maybe we should start there. Find an a that for theta is 0 has some biggest number, up to you to decide what that number is. And then for theta is pi over 2 is some smaller number.
That would be a sine.
Yeah.
I guess.
Some kind
Yeah,
of
is
sine.
it a sine though?
A
But then you
sine
have zero.
squared maybe.
Maybe. Well, that's well. There's differently shaped eggs, right?
Maybe a sine plus a
Biology.
constant or something.
It's up to you.
So it's never zero.
And every choice for a as a function of theta will give you a different shape. And just like eggs come in different shapes, ask a biologist. I'm sure that's sure we can find something.
This is a very open question.
Yes, that is the fun part of it because it's
You
a
could
free range exercise.
Yeah.
Yeah, you see where this is going, yeah?
You see the fun?
I would guess a sine squared, maybe with a constant.
I feel like a good joke went too late here. I appreciate that. Good.
I didn't hear it. Say it again.
It's a free range exercise.
Now you overdid it. You didn't have to do the exercise.
That's what made it
but
funny.
you didn't pick it up, so I felt like you should have.
Now you.
No overemphasis.
Okay, well, if you have to explain the joke, then not as funny anymore, right? Okay, good.
Shouldn't be a cosine though, since we start at 0 with a being.
Actually, I think I agree
A
with that.
being a
Yes.
maximum of 0,
Yes,
yes,
yes.
a cosine.
Oh,
But a
okay.
cosine squared because a is never negative.
Okay, but be careful there because the cosine at pi over 2 becomes 0. And you
So
don't
that's how
want
we have a constant.
So you maybe should add a constant. How about
Yeah,
take
shift.
a theta, make it some number plus cosine
Yeah.
theta. That sounds like a good choice.
Okay.
Great.
So.
That number can be.
It is cos squared, right?
Why?
There's no negative a.
Yeah.
Yes. I think there's multiple choices. You can also say cosine theta and the absolute squares or something like that.
Plus c.
Is this the way you arrive at a function of theta of a, but just by like trial and error?
Yes.
Well, again, it's no pun intended this time, but it really is a free range exercise in the sense that it's up to you to find something that resembles an egg. So I guess there's more than one way of doing it. But I have one objection to this particular choice of A, and that is that it will give you the same answers for pi bigger than pi over 2. Right? If you go further than pi over 2, the other side will be
symmetrical.
Symmetrical in the xy plane. And I think one of the defining properties of an egg is that that doesn't hold.
So after greater than pi over 2, a is bigger than the corresponding
I think it
angle
will
on
be
the
smaller.
outside.
I think on the other side of the egg, the distance
smaller.
should be a smaller
Yeah.
number.
How do we put that in function form? Maybe c could be a function of theta as well.
Oh.
The constant that you add to the
Yes.
cosine. Yeah.
I didn't get anywhere at home with this, but now like I'm thinking maybe like if you visualize the shape of an egg, it's maybe like if you think of the top part of it is more like an ellipse, while the bottom half could be approximated to like a sphere, like half a sphere.
Sphere.
Oh,
So you
okay.
have like a as a function of theta, a combination of a
Yeah,
sphere
yeah,
and
yeah.
then on the top an ellipse.
That okay. So you're saying that at the moment that you go beyond pi over 2 for theta, from that moment on your a should be approximately constant.
Yeah,
So at the moment
Basically.
you've gone through the xy plane,
exactly.
then from that moment on the distance a is almost constant. So it gives you a spherical underdome or something of the egg.
Mm.
I mean, it's not a perfect egg, but it's going to be approximate.
Yeah, sure.
That is a step function.
You have to be careful that you glue them continuously together, of course, at the junction.
Yes.
But sure, yeah, you can do this. Yeah, step function, sure.
So that's one option. This is another option.
Put an equal
so
somewhere.
this would be a circle. So
Add
that's
it.
just sine.
Put an equal somewhere on one of those. The two.
Sorry.
Smaller or equal on one of
Okay,
them.
yeah. What is it for a normal sphere again?
A is constant.
Yeah, so
Yeah, true.
So you can just equal C.
Yeah. To determine. Okay. And for an ellipse, it is a function of theta.
I think you put in the capital A.
Oh yeah, this is the square.
So yeah, so cosine squared theta.
Cos squared theta
Yeah.
for an ellipse.
You want to make it an ellipse? It's up to you.
I think we can approximate the top that does an ellipse, but I forgot the equation. approximation for new.
No, but you already have a nice approximation, right? Isn't it that the first option here, cosine theta plus some constant?
Oh, this part.
Yeah,
Ah, yeah.
that certainly works.
Yeah, because then how much you shifted is proportional to theta, but actually it should be anti-proportional because as you approach pi over 2a, it gets smaller.
Yes, but it becomes smaller and then you're subtracting a number still. I'm not against it, I'm just parsing what that would entail, this particular choice.
Well, because a is not 0 and because cos goes to 0,
Yes.
we have to add. Oh, yeah, I see.
No, but what I'm seeing now is that if you go to pi over 2 for theta, then the first one becomes 0 and then you're
Yeah,
subtracting
and it's-
something, you get a negative.
Can we add can we make the constant alpha, a, not alpha? So we have cosine squared theta plus a. So when theta becomes pi over 2, you have
Oh,
a.
that would make it continuous.
Mm-hmm.
Yes.
Wait, say that again?
Like make the constant a.
Yes.
The
Like
same one that you're
constant
using.
that you added. Like.
This constant.
Yeah.
Make it a.
No, the whole thing, I think, right? No, not just a times theta, but
Yeah, just a.
Yeah.
just a. I mean, what you're writing down now with the plus constant a?
This a
The big
or
A, yeah.
this
Yes.
a?
No,
The big one.
Big
The big
A.
one.
Yes. So,
Yes, because then it would be 0 plus a at the
yes.
boundary.
So at the junction of the two, they continuously match. Yeah, I mean this looks fine, I guess.
Mhm.
I mean, for theta smaller than pi over 2, but that thing that you had certainly will give you something that looks like this. So yeah, that works, I guess. Okay, good.
And it doesn't have to be cos squared theta anymore. It's cos.
Because you're sticking to the range between 0
Uh,
and pi over 2
mm,
anyway, right?
No, but if you go backwards, then.
Yes. Yeah, that is a
No,
point.
but cos minus theta is cos theta because it's a.
Yeah, but you don't have a minus. You don't put in minus values for theta. After,
Well, if you are here.
oh yes,
This quadrant.
yes. This is theta is pi over 2. This is theta's pi. This is
Yes.
theta 3/2 or times pi. That's
Yeah.
still a positive number.
Yeah. But that it wouldn't matter in that.
No, it would.
It's in the bottom.
It would. The cosine of this number is negative.
Which
Right.
quadrant are you talking about?
Here, this here is theta is 3 pi over 2.
Okay. Yep.
And this is pi. This is 3 pi over 2.
Yep.
The cosine of 3 pi over 2 is well, that actually 0, so it's a bad example, but
Mhm.
But when you're in the
But then-
bottom,
Yes.
we don't have the cos anymore. We just have the constant a. So
No,
you
we
don't
should,
have to worry about negative values.
no, that okay, so that's true. So that
Yes.
means it will.
We only care about this quadrant and this quadrant for this part.
No, I agree.
And in this quadrant, it will always be positive. In this quadrant, you have a negative theta, and cos of minus theta is just cos theta.
No, but you don't have a negative theta here. This is not negative theta.
It's not.
Oh, as it measured from this side will be the negative theta. Oh, I see.
That would be bad.
No, I think you're right.
Then the squared is
Yes, okay.
redundant.
You're right. No, sorry, you're completely right. Yes, yes. Okay, good. So, okay. Yeah, but you know the difference between square, the cosine and cosine square isn't just where or and if there are minus signs. It also tells you what the slopiness is. Right?
Yes, yes.
So you get a slightly different shaped x with or without the theta, the square.
Yes.
why
But
would you-
initially, sorry.
Continue.
I'm just saying initially I only put the square there to stop it from being negative.
I know. I mean, we don't really need it. Is what
Yeah.
I'm saying now. Good.
But why is that? Why do we need the square thing?
Okay, so in this quadrant, cosine is positive. In the bottom, we don't care because there's no cosine.
Yep.
In this quadrant, eta is negative, and because cos is a what's it called when it's symmetric about the y-axis?
Even.
Even.
function.
Because cos is an even function, cos of minus theta equals minus cos theta.
Okay. Yeah, I see.
That works.
So we don't
So the function should be from 0 to pi over 2 and then from 3 pi over 2 to
yes,
2 pi.
back to 2 pi. To
Yeah.
2 pi. Yes. Michaelis' point is that the ranges that you have to be extended.
Another function which is just a constant. Connects.
And the particular choice of this extra constant
Yeah.
plus a, to make it capital A, make sure that at the junctions they agree again. So you now have a continuous function. It's also differentiable, by the way, so that's very good.
2 pi, you're gonna get a 3 pi over 2, no? You want to keep it constant until 3 pi over 2, not
Yeah.
2 pi.
Should be 3
Uh,
pi
no,
over
it's
2.
just the 3 pi over 2.
My bad.
Instead of a, if you have to add like this.
And then on the up for theta bigger than 3 pi.
Yeah,
over
bigger than 3 pi over 2 to 2 pi.
Then it's still a cut.
That's 4, then we can say this can
Great.
then we'll have one part here.
This is okay. This is fine. Good. Okay. Great. I think we have the theta shaping this down now. Yes.
The relation between radius and angle.
Yes.
Yeah.
Now then there was the F business. So I think the A theta business is now completely checked.
Anyone else want to take over a whiteboard?
I want to try doing this thing that they did.
Yes.
Like analyzing. So I'll just like use more colors so that the things get less confusing. So first I only have the 2 points, P over here and Q over here. That's ds. Now P is the one defined at c sine phi, so you have this is theta, and phi would be,
You can dot it. Do it.
yeah, for sure. Okay. Okay. And then now the z phi and the dt would then be this. I mean, not this one, and if I can say that this is u, this one is d phi. Now, like one of the other steps that they did when they considered the sphere was to like, I don't know, use the radius as well. To try to find some relationship between the distance and like the values that you have around it. You're trying to like, I remember you're trying to make a triangle so that you can express it too.
Just my understanding then.
Yeah.
What we're doing here is are we looking for the function f? So is that your objective here?
Well, I was trying to express ds so that we could see how the
Oh, I see. Okay.
how the f is expressed.
Yeah,
Should
yeah.
you not start by getting the s and then from there get the function?
No, there's 2 ways, and your approaches are both correct. You just his starting point ends up with yours, and your starting point ends up with his. Both is fine, of course. So his idea is, well, maybe I can already by looking at the picture find out what f should be, and yours would be choose an f such that you end up with symmetric tensor.
Gideon, what is the difference between a theta and f theta? Because a theta is giving you the whole shape, right? With respect to the variable theta, but what is
Yes.
f theta?
Well, maybe that's a good question. What is the physical interpretation of f theta in this expression? It's not quite the same as A theta because A theta multiplies everything and F theta does not.
Maybe it has to do with the coordinates you're taking.
I think that is correct. But it says a little bit more. The fact that F only depends on theta, not on phi, also has particular physical meaning. Namely, what's the word here? A symmetry around the z-axis.
Yeah.
Right? The fact that at any theta, any particular value for theta. So if you stick to one particular theta and you walk around there, then this is zero by definition because you stick to one theta. The fact that this might be something different, but it does not depend on phi, means that sticking to one particular theta, it doesn't matter where in phi you are, you will get the same answer. It's another way of saying that at any theta you should have circular symmetry around for phi.
It's basically doing the radius is expanding.
Yes.
As you go
It's giving
down.
you the width of the A.
Yes, exactly.
The circumference.
Yes. But that means that it must be related to A in some particular way, right?
Yeah.
Because A is this number.
Yeah.
I think this, this radius is A squared times F squared or something like that.
Really?
Yeah, something like that. I'm just thinking out loud. But it is clear to me that this F has something to do with the circular symmetry around the z-axis. And I think in order for us to understand how we should pick F, maybe we should think a little bit about exactly what F does in our line element. What role does it play physically? One thing again we can see is by the fact that it does not depend on phi, is that it designates, at the very least, it designates circular symmetry around the z-axis.
It depends on your height on the egg.
So then that would mean that this is one, for example, and then you have over here.
Yes.
But the same function.
Yes. Yeah.
But is it the circumference or?
Yeah, I don't know if it's that's the way to
Area,
express it,
that's-
but
Yeah.
that's what it repeats.
Yeah, but they are related to each other, right? A and F. Because,
Yeah, closely.
let me draw, with yet another color. At a particular choice of theta, you might end up with this particular circle, yes? With a particular circumference. Now, at a different theta, you would have gotten this circle with its own circumference. But this distance, just as in the previous exercise, determines this circumference, agreed? That was the exercise that we did before with the perfect sphere. That the circumference, this circumference, is related to this distance in some particular way. And this circumference is related to this distance in a particular way. So I can immediately tell that there is a relationship between the circumference. In other words, if you integrate over phi from 0 to 2 pi, and this distance, but this distance it has something to do with A. So I can sort of guess that my A's and my F's are not completely independent. Once I specify, let me say the same thing in a different way. Once I specified my A, that means for this circle, that's this number, right? I've also specified my circumference. And this circumference has something to do with this integration. So, do you agree with this?
Yeah.
At the moment that I stick to this circumference, and this is 0, the amount of meters for that circumference is then the integration over the phi part, and it comes multiplied with this f.
And the A as well, right?
And the A as well.
Yeah, it has to do with the relationship of the angle with what was it? It was so you can express the angle with one segment of length that you have here plus the length towards the center of the circle.
Yes.
So if the center of the circle is at the pole, and this distance is d, your angle theta for this one is going to be theta equals a d under, let's say, but then you need another segment, so it has to be the circumference that we're talking about, no? That's its inverse. I don't remember exactly, but there was like, you can express the angle with the circumference and the distance from the center.
Let me just
It
for
is.
fun do this exercise for a moment. Suppose I stick to this particular circle here, okay? And I calculate, so let's call it circle 1. Its circumference, according to this expression, is going to be this integration. With the ds, with this thing 0 now, will give me a squared theta, this unknown f squared theta, d phi, this is going to drop out. It's going to be this, right? This is the circumference of circle 1 in the way that the metric tensor now has been expressed. All of this is theta dependent, so it comes in front of the integration, so I don't have to care about that. And one time around this one will give my 2 pi. Agreed? How about the radius? I'm really just redoing the exercise that we did before, just for a different. So this is the radius. Looking at this expression, again, that's going to be ds. Looking at this expression, I'm now sticking to a fixed d phi, and I'm integrating over the theta. So I will get
A theta.
a theta d theta, right? Okay. Now we can actually do this integration because we have chosen our own thing here. And this will give you, well, I'll just do the integration, something will come out. But the final expression
Depends if you're in the first half or the second half.
yes, that's of course true. I'm restricting myself for this visualization on this half for now.
Yeah.
Let's call this the phi 1, as in the theta 1, the theta that corresponds to this particular circle. The expression that you will get will be something that only depends on theta 1. This is true, yes?
Yeah.
But that means that whatever this expression is, you can use it to eliminate this guy's theta 1, and you will get this c as a function of this r. I think that's correct.
Okay.
That hasn't fully specified yet. I was looking for a necessary relationship between f and a, and I'm not finding it quite yet. You know exactly what a does. A makes sure that this particular shape comes out. The upper shape, that's this, and the lower shape, that's that. What does f do?
Basically giving us the
Yes, because of course you can have an egg that has a particular upside and downside with a particular radius, but still at every phi might be bulging out or something like that.
how big is it, right?
Yes.
In the sense of
How
width.
Yes.
Okay. Yeah.
So, what do you mean with it?
Yeah.
Is it giving you just a circumference?
So the x shape in a theta is just for the two-dimensional case, but the f theta is giving you already the 3D, how it looks in 3D. So how big the egg is gonna be.
But
Big
it's
in
not.
what sense?
Big in the sense that the diameter of the circles that compose
The circumference.
the egg.
Yeah. Okay.
Yeah, that's quite literally what we're writing down here. Here. Because even if you have specified what a is, this number for a particular theta 1, your circumference might be bigger still depending on your f's. So it's not just this A that determines the circumference. It is also determined by this additional factor f.
I still don't see that.
Well, here's your formula for the circumference, right?
Yeah.
That's this. And the circumference, the amount of meters that you have to walk at this circle to make one full revolution,
Yeah.
is not just given by your choice of A.
Yeah, that's true.
It comes with an additional amount.
Oh, that's just by integrating what we are given for ds squared, right?
Yes.
Yeah.
But that's how I got there.
Yeah.
So just from this expression,
Yeah.
I can tell that just specifying our A, as we have done here,
Mhm.
will not fully specify the circumference yet.
Yeah.
So that's what f does. It adds to the circumference. Note that it does not add to this radius. Okay? So I think we were homing in now on interpretation. What does A do? According to this calculation, I mean I haven't gone through it in full detail using these expressions, but according to this expression here, I can tell that this distance from here to a particular designated circle, its radius, that one is fully specified by our choice of A. That's what I see here. Okay, so A is a function that tells you how many meters you have to walk from the North Pole, if you will, to whatever circle you're interested in. That's what A does. F does a little bit extra still. F tells you how many meters the circumference is, or if you will, how wide it is.
Using that A.
Yes, given that A.
Because A depends on theta, and
Yes.
so does F.
So the A specifies how many meters from here to there. And what we find now that even if you know how many meters it is from here to there, the circumference, yeah, I know exactly what, I know how to visualize this. Look. You give me A, yes, as a function of theta. That means, according to this equation, I know how many meters it is from the North Pole to a particular circle. Agreed? Let's suppose that circle is here. And so let's suppose that this calculation gives me 5 meters. Okay? I can draw another circle starting on the North Pole that takes me 5 meters to get there. Agreed?
Yes.
I can also draw, well, let's do it with a different color. I can also say, you know what, I'm going to take my 5 meters that comes from here, comes from my definition of A, and make a different circle. I'm not very good at drawing, but I'm trying to draw a green line that is also 5 meters, but just spreads out a little bit more. It doesn't go down as much. It spreads out
It's
more.
a dome, but with a depth.
Yes, exactly.
Yeah, that makes sense.
So what we're finding here is that just specifying A will only tell you how you get from the North Pole to a particular circle, but it doesn't tell you how far that circle is from the z-axis. You need extra information from that. That is what F does. Because that's what you see here. You have your A, but you still need F. That's what it does.
I thought A was like the distance from the center of the egg to the surface.
Yes.
Why that? Then why are you like saying that it's from distance from the North Pole to like the circle?
That's what I see here, right? I see that if I want to calculate how far it is from the North Pole to the circle,
Ah, okay.
I see
From
that
the
it
radius.
will be dependent
Yeah,
on my A's.
It's just the difference.
Okay,
Yes.
yeah.
So, does that mean that f theta is going to be like an ellipsoid in the one hemisphere, and in the other hemisphere is going to be a semi-sphere?
I think so, yes. So I don't know yet what the answer is, what the best choice is for F to make it look as egg-like as possible, but I do know now what the difference is of the two functions in the shapiness of the egg that comes out.
Yeah.
That's a fun exercise, really. It really is. I mean, it really required us to think what do things mean in the metric tensor. So in that sense,
That was fun.
no, it really is, right? I mean, in that sense, having a free range exercise really is beneficial educationally because it forces us to think what do things mean. I think we're out of time, right? Okay. So you know what? Let's see what I have. Let's see what my egg looks like. Okay. Yeah, okay, so this is what I got from my egg. But anyway, as we can see, there's one of many choices.
We get an exact.
Where? There.
4/pi² theta squared sine squared theta.
Where does that come from, though?
Yeah, let me check.
Will you post these on Ethereum?
Yeah, but this is not gospel, yes? This is my particular interpretation of this free
Yes,
range
but it
exercise.
would be interesting to see how else.
Would
you
an
could do
exercise
it.
like that be in the exam?
How much can I say without giving away what the exam is? But I will tell you something. What I will give you is a metric tensor, without saying where it came from, and it's up to you to decide whether this is a curved space-time or it's just a flat space-time in sneaky coordinates. Okay? Choose your method. Maybe you want to draw a circle, check whether the area is pi r squared. Maybe you want to draw a triangle, check whether the sum of angles is 180 degrees. There's one exercise where I'm just going to give you, here's a space-time, here are coordinates, calculate for me what the metric tensor is. And there's a contraction exercise, just on the mathematics of contractions.
But I still don't understand how we can know from metric tensor, like if it's curved. Like we can write the right element from the metric tensor, but then like what? Like how do we know?
It's like you try to describe the space
Yes.
with the metric tensor and you see
have
if...
to integrate the path.
We saw an example just today where we saw that we had a metric tensor. Now for that we knew that it was curved because it was given as an exercise, but suppose that you didn't know that. And for that particular one, we drew a circle and then we calculated whether the circumference and the radius of that circle were related by 2 pi r, and we found that it wasn't.
And it was not, so it was not a like...
So it was not a flat space.
Oh, so we can find like S and then like from that,
Yes.
like whatever.
This is a statement that we were discussing earlier, that the metric tensor will give you, after some work, your flatness. Not at a glance, but after having tried some flat space thingies, see if it comes out. Okay guys, thank you for your contributions and your time. Also thank you for indulging us.
Are we gonna see the Riemann tensor in the course?
Yes, but we're not going to use it to its full effect, but I'm going to show it as a Minkowski check.
And are we gonna also not derive, but maybe come across the cosmological constant?
Yeah. The final lecture, number 6 in the series, is about general relativity applied to the universe as a whole. And cosmological constant will automatically come in there. I don't even have to put it in, it comes out.
It comes out.
Yes.
So is it gonna be like, are we gonna like ever do like that really big equation of like 8 pi r or something?
That's the isomorphic equation. Yes, I'm going to flash it to you, but we're not going to actively do it. That's PhD level stuff to work on. And I can attest to that because this is how I got my PhD, by working on exactly the equations.
Many chapters and
Thank you.